Log on, tune in, find out. Another good idea from Cambridge.
Alessandra Giovagnoli, and she's going to talk about recent developments in adaptive design of clinical trials to account for individual and collective ethics.
Well, the usual thanks to the people who invited me, Rosemary and Basha, and to the Institute for this very pleasant visit that I'm going to have. In the middle of Bill's talk, I decided to run away. And then I came back because he was giving my whole talk from one point onwards. So there's a lot of overlap and repetition, but that's towards the end mainly, I think. The other thing I have to apologize about is the rather pompous title of my talk. It's much more modest than that. I'll tell you what the idea was. My co-workers and I had a couple of papers, and earlier in this meeting we heard about the difficulties of communication between statisticians and those who operate in medical care, and believe me, there are no other Italians here, but in Italy it's much, much, much worse. So we thought in a... So we were rather naive, I think, and we thought, none of our colleagues in the medical world are going to read our papers in Biometrica. I mean, then perhaps they don't even know that Biometrica, but if we explain it to them in very simple terms and give them a lot of very simple examples and get this published in the poor Italian version of statistics in medicine, which is called Biomedical Statistics in Clinical Epidemiology. It's an Italian journal. So if we get it published, and then they will know. Well, as it happened, other things. We decided to do other things along the way. We started looking at a lot of little examples, but we feel that this paper is. We fell between two stools, and the Italians say it's neither meat nor fish. I hope you're all vegetarian, so we can go. Okay. Okay, that's the English, the correct English. Before I start, adaptive. Okay, we heard so much about adaptive. One definition was adaptive randomization is to assign with higher probability to better performing therapies. This would be all right for my talk, but I think it's too restrictive. I prefer Basha's definition. This is from her talk. Adaptive design, the information is gathered sequentially. After each step of the trial, the statistical model is updated. Next step of the trial depends on all the results up to date. The trial is stopped accordingly to pre-specified stopping rules. In fact, I was suggesting a few years back an even more general definition, which is the one below. An adaptive design is a sequential rule that uses previously gathered information for choosing at each step in a deterministic or randomized way which treatment to allocate to the next patient or group of patients and whether to stop. And I felt this was so general that includes everything, including group sequential. Another point that Bill has made is that if you take this definition, then a design will, in general, be a stochastic process. You learn about it. I mean, the experiment is the realization of your stochastic process, so the design itself behaves like data. Therefore, I tried to suggest that when, if your allocation and or stopping rule, your allocation can adapt to the previous information in several ways, and if it's only the past allocations, like in evidence-based co-design, for instance, then maybe we should use design adaptive. Bill says restrictive randomization. Okay, so I've lost. He wins. Maybe it's restrictive randomization. Otherwise, when it adapts to responses, we call it response adaptive, so data dependent. Then there is the doubly adaptive designs that Bill has talked about, past allocations and responses. Covariate, what do we say? I realize, this Rosemary's point, that when people talk about covariate adaptive, they mean something different. So maybe we should choose different expression. And then, of course, you can adapt to everything. Past allocations, responses, and covariates. I should mention a lot, I should quote a lot of papers, especially Anthony is looking at me for not quoting his work on covariates. But my co-workers will kill me if I don't say that they too have a paper in Biometricum and covariate adaptive. So there it is. Now I can start. Basically, this talk is divided into two parts. The first part, I talk about what Bill calls targets, and I call target 2. So it's desirable treatment allocations with respect to some criteria. In my case, it will be a compound criteria. I, in fact, have two different criterion. And the second part will be about how to get there, so how to implement these targets with the double adaptive designs that Bill mentioned. Covariates. There will be a last part about covariates, a short one. Okay, some notation. It's different from Bill's, of course, because we didn't interact before. Instead of A and B, I call it T1 and T2. Two treatments for simplicity can be extended to more, but I want to keep it very, very simple. Again, the same assumption. I think you made that too. I can't remember. Given the past allocations and the data, the responses depend only on the treatment and the covariates of the patient. So no correlation. In other words, we don't observe the same patient repeatedly in with this model. We could assume an exponential family for generality. I don't want to do this. I want to be very, very simple. So I just talk about mean and variance of the responses. And basically, I want to focus on normal responses, homostochastic, heteroscedastic, or binary. Then we can also introduce the dependence on the covariates, of the mean responses on the covariates. Okay, so let pi be the proportion of allocation to treatment 1 after n observations. We either want to estimate or to test the treatment effects mu1 and mu2, and in general, the variance covariance of the estimates will be either exactly or asymptotically diagonal with this very simple expression. Treatment allocation, the ideal treatment allocation in optimal design theory, it depends on your design criterion, which I measure loss of information or utility, depending which way around you go. Okay, let's say loss of information. And so the basic allocations are either balance, if you choose the optimality. It means you're interested in all in both the parameters in the same way, or the Neyman allocation if you choose trace, or in this case the same as C optimality. This does not take into account ethical costs. Bill made this point that the Neyman allocation, because it only depends on the variance, it could be very bad, because if the better of the two treatments has got smaller variance, you would observe that treatment very infrequently. I think you said something like about the variance. Okay, so how do we measure the ethical loss? Bill mentioned this. Okay, Bill is given my talk, as I said. Okay, it's either the proportion of patients who receive the worst treatment. That's one way of doing it. You can always choose this as your criterion. or in the binary case, the expected proportion of failures. These are used in general, except that the expected proportion of failures is related to the previous one by a linear transformation, so sometimes the two are basically equivalent. One possible approach is not the only one. There's a lot of literature on this, including Anthony and Atano Beersvers and many others. A possible approach is to minimize a weighted average of ethical loss and inferential loss. And clearly you have to standardize to make them comparable, to let them vary between 0 and 1, both of them. Is this approach equivalent to Luke's? Luke had a constraint, or Bill's approach with a constraint. In this case, yes, it is equivalent, but I think it's only because one of the two criteria is linear. In the nonlinear case, it may not be equivalent. I did the calculations a long time ago, so I don't remember the details. So let's take a compound criterion A. This is, it's all right for all your models. And we choose as an inferential optimality either the determinant of the trace for simplicity. We standardize it by this transformation, which is there. No, maybe I can show it. Yes. This is a transformation we choose, so that now they're both between 0 and 1. For binary, we could choose, instead of the proportion of patients who receive the worst treatment, we could choose the expected number of failure. Like I said, the two, minimizing one is equivalent to minimizing the other, so it's not worthwhile considering criterion B. Criterion C, which is only for the binary model, is different. And the reason why we have two criteria, A and C, is that we have two papers, and one has looked at A and the other one has looked at C, so we wanted to have some sort of comparison. Now we minimize with respect to the allocation, to the design, and the optimal allocation will depend on the unknown parameters. What about the weights that we use for averaging? Well, we got to choose the weights. They could be fixed, or they could also be a function of the unknown parameters. We want the weights to deal with both treatments symmetrically. And another requirement, which seemed to make sense at the time, was to have weights that are increasing in the difference between the treatment effects. So that if you have a small difference, it doesn't matter so much, you know, which patient receives which treatments, if they're more or less equivalent. But if they're very different, it does. And of course, you don't know. The parameters are unknown at the start, so the weights are functions of the unknown parameters. And maybe it's functions of something else. So what do we get by doing some very simple calculations? We get a solution in the case which we take criterion A, and optimality is d-optimality, which only depends on the sign of the difference of the treatment effects, which one is better than the other. Observe that we want this, usually we want this target to be less than 1. That means that we don't allocate all the patients to the same treatment. And in order to, in this case, in order to ensure that the weight omega, which is the one we put on the ethical loss, should be not greater than 4/5. Otherwise, we overshoot, and then we say give the better treatment to all the patients, and that's it. What do we gain by taking a positive weight? In other words, well, we gain something and we lose something. We gain that there is an increase in the percentage, well, there's a decrease in the number of subjects assigned to the worst treatment. And so we take the relative decrease as a measure of our ethical gain, and we take our criterion, inferential loss, as a measure of the loss. So in this case, the determinant. The maximum difference is at 1/2 in this case, which seems to indicate that equal weights, fixed weights, 1/2 and 1/2, is maybe a good thing to do in this case. Now, this is a different choice of the weight function, which seems to me to make sense. If the difference between the two treatments is 0.5, half the standard deviation, then you would choose a weight of about 1/3 on ethical loss, and you will get an optimal target which is not far from the balanced one. On the other hand, if it's equal to one the standard deviation, then your weight will be 1/2, and your target will be 63%. I think it's reasonable. On the other hand, with the binary case, the weight function, a linear weight function, which simply is the difference between the two probabilities multiplied by 4/5 in order not to overshoot, it seems to me to be not sensitive enough, because in the case of a difference of 0.2 between two probabilities, which is fairly large, it's not very sensitive. It gives an ideal target of 0.52. It's about the balanced one. So maybe we should change the weight function in this case. But at least you have an idea. Now, trace optimality. Trace optimality, the solution in closed form. First of all, if trace optimality is done with equal variances, homostochastic, then it's the same as the determinant. Nothing changes. So you have to assume the heteroscedasticity. The solution is in closed form. It looks complicated, but it's not much more complicated than Neymann's allocation. When omega is 0, if this bit disappears, and you get back to Neyman. So if you put no weight on ethical loss, you go back to where you were before. However, there is a condition. This condition ensures that you're inside the 0,1, and you don't. I mean, this is a condition on the weights. Because in general you don't know the variance, you don't know if the condition is satisfied or not. So unless you have an idea what the variances are, omega less than 1/2 is sufficient, but it may be restrictive. Maybe you want to put more weight on the ethics. So there's no way around this. Some comparisons. The first group of calculations are for when Neyman performs very badly in ethical terms, because it gives very few observations to the better treatment. Our a compound optimal criterion doesn't do much better for small values of the weight. You have to go up, you have to increase the weight, have a large omega to get out of this. And then, of course, if you increase it too much, it gets too large, and then you get one as a solution. So it's not entirely satisfactory, I must say. Unless we decide to choose a weight that depends also on the variances. That may be better. So our initial intuition that the weight should depend on the difference between the treatment effects, maybe it's not enough in this case. You also need dependence on variances. Ethical loss, well, relative gain by using the weight. You always gain something. You're always doing better than by not using weights at all. And how much better depends on the values of the variances, of the standard deviations. So in some cases, not much better. In some cases, is a lot better. Now we move on to the binary model. The binary model, again, we're comparing the case where when Neymann's allocation is not very satisfactory with the optimal compound, and in general the optimal compound weight doesn't have this problem. It's more than half. But in some cases, even if you're being optimal with respect to the compound criterion, it's not good enough, and you're still under a half. You're not ethical, so to speak. Okay, now I change to the other criterion, which it was, instead of taking the average, I take I take the harmonic mean of the two criteria, which is what was done in the Biometrica paper. In this case, the advantage is that we can give conditions for the target to assign more subjects to the better treatment. With the optimality, the answer is always. With trace optimality, the answer is if the weight function is chosen suitably. You see this in the following table. There are no reds, everything is black, meaning everything is more than a half. Now move on to part 2. And this is the part about the doubly adaptive biased coin design. Because the target allocations depend on the unknown parameters, we may want to define adaptive randomization rule so that the experiment converges to the target. There are many, many ways of doing this. There are some advantages in using doubly adaptive biased coin designs. And with doubly adaptive, you get an initial estimate of the target, of your target, and then your probability of assigning first treatment to subject n+1 is a function that depends on this dissimilarity. That is, it's a sort of measure of the dissimilarity between the present allocation and the target, estimated target. Well, a special case, Bill was pointing out that, is when you don't need to estimate the target because your target is a half, it's balanced. So that's a special case. You can do that as well. Some conditions on the function, though, are needed. We want it to be continuous, so that rules out the example that we saw at the end. Continuous may be too restrictive, because I agree, you know, the best solution is not with a discontinuous function. Then if the present allocation is the same as the target, we want to use that as the probability, randomization probability. We want the function to be increasing in the estimated target and increasing in the ratio between estimated target and present allocation. So in order to favor more the treatment TI if it's much smaller than the estimated target. And then there is a condition on symmetry, to treat the two treatments in the same ways. In other words, if I change the labels, nothing changes. These conditions are basically what Hu and Zhang assumed, except they didn't make the last point explicit. But they used the function which satisfied the last point. So I think I might as well say that this is what we want. All right, so that if that happens, then we can it can be shown, it's not non-trivial to show this, that the design converges and the estimators are consistent. It certainly it requires some effort to prove this, but it's true, and so we're happy with that. Special cases, sequential maximum likelihood, Bill explained that. So we don't look at the present allocation, we just look at the estimates of the target and use that as randomization and probability. But it's got these advantages. One example, if the estimated target is 0.7, the probability of assigning T1 is 0.7, both in the case that T1 at present has a frequency of 0.05 or 0.8. In both cases, you say probability is 0.7. And then the function that Bill showed, the one by Hu and Zhang, is already said that gamma is a measure of randomness, and when gamma is 0, this is the sequential maximum likelihood design. I don't know if this is very useful. I was surprised because Bill said that the Hu and Zhang design is all right for gamma between 4 and 7, 2 and 5. But it seems to me that it's pretty bad at 2 already, because in a lot of cases it's deterministic or near deterministic. Once we have 0.999 a lot of times. So that's the disadvantage with this design. We tried a different proposal. Oh, a bit of the formula is disappeared. Instead of using the power y divided by x to the power gamma, we use a different function, the so-called error function. And if you do that, you just change the formula and use the error function, it seems to me that you get more friendly randomization probabilities. That's the last column. They're not so extreme, not so deterministic. And of course, you have to actually check that the conditions on the G function still hold, of course.
When I talked about gamma between 2 and 5 with respect to power.
Okay.
I wasn't talking about with respect to application.
No, but you did say that it gets deterministic at some points. The design that
As gamma gets larger,
it's
it gets more determinate. You lower the variability, but you increase power.
We didn't at all discuss randomization. quality of the randomization did you build? Is that right?
No,
No,
I didn't discuss
that's
that at
just-
all,
yeah.
no.
There are some simulations, very few, that we've done. We've simulated this procedure, the doubly adaptive, all three methods, doubly adaptive methods, in all the cases that we had defined before, considered. Normal responses. Normal responses, I have very little to say about that, because we know already that the simulation doesn't show anything in particular. The first lot is sequential maximum likelihood, which seems to perform worse in the other ones, but this is a theoretical result. It was shown by Hu and Zhang that their design is better than sequential maximum likelihood. It's got smaller asymptotic variance. This is method 3. The method 3 is more or less equivalent to method 2.
I'm sorry, I can't tell what you're actually plotting there.
Sorry?
Can you repeat what you're plotting there?
You
I'm
want-
not sure what you're plotting there.
The design.
Yes.
We have a target,
Yes.
and the allocations go up and down with respect to a target, but they converge eventually, but very slowly.
So you're plotting
know that.
convergence to the target.
Yeah, it's very slow. Not the estimators,
Yeah.
nothing like that. Just the design, convergence of the design to the target.
Yes.
These are the simulations for the binary case with just one lot, the A criterion, the changing various values of the probabilities, and also changing the weights. And so you get different targets each time. I'm not sure what the simulations show. I'm not a simulation person. I think that simulations are inconclusive. You look and you know more or less what you knew before. So I believe in theorems. We don't have a theorem. So okay, let's go on to the third part. Yes, this is very, very short. Assuming we have one covariate, fixed levels, maybe it's binary, men and women, and assume the variances are the same, homoscedastic. Assume also that the distribution of the covariate in the population study is known, and assume that we're not interested so much in this covariate effect, but we want to estimate the treatment effects or compare the treatment effects. So after a little manipulation, we get two criteria, one for inference and one for ethics, inverted commas. The one for inference is the average information loss measured by the variance of the estimators over the covariate distribution. And the ethical loss is percentage of patients assigned to the worst treatment. So with these two criteria, we get an average compound criterion phi, and not surprising to me, at least, the result is the same. The result is the same as in the no covariate case. Why? Because of a model. In our model, there's no interaction between treatment and covariates. So why should it be different? So the answer is the same. So we don't have to give any examples. All the old examples are still true in each covariate group. The same optimal allocation in each covariate group. However, implementation is non-trivial. And because I thought that I was going to run out of time, I haven't put in the details. They are to be found in the paper by Bali Antonini and Zagoreu. The fact that you have covariate groups forces you to change the doubly adaptive design to allow for different frequencies of the covariates in the population. Otherwise, some groups would be underrepresented. Therefore, they have some results with by using different gammas of the Huang-Zhang algorithms in the different covariate groups.
So using different gammas in the different groups, is what you're saying?
Yes, they use Huang-Zhang, which has got a gamma.
Yeah.
Gamma is the degree of randomization. They use different randomizations for each different covariate. So if a woman comes, they use a gamma, another gamma for men. And this...
Well, what is the point of that?
You don't know why they do that.
No.
In case
You tell
there's
us,
a
please.
strong imbalance, because they're trying to achieve balance, in case there's a strong imbalance in the population between the covariate
yes,
groups.
yes.
Okay, Sandra, so let me see if I've understood this. You've got a covariate that just partitions the population,
Yeah.
and effectively you're running your randomization procedure separately within each block.
Yeah.
Is that right?
Yes, that's
Okay.
right. But with different values of gammas in each
Yeah.
block.
Thanks.
Proportional to the frequencies, or so
yeah.
as a function of the frequencies. And,
So this is my conclusions. Okay, so if we're faced with a practical problem, what do we have to choose in this case? In this outline, you have to choose between the determinant and the trace, but that's well known that the choice depends on whether you're interested in all the parameters or just the difference. And same for testing, of course. It doesn't matter if you choose receiving worse treatment or expect a number of failures. We have two compound criterions. Which one is better? I don't know, but I think the first one makes more sense. And it's easier. That's one of the things that we have to keep in mind every time. You know, I'm one of those who believe that 3 + 3 and Efron's coin and randomized play the winner are popular because they're simple. So I would choose the simpler of the two. Doubly adaptive randomization, yes, but possibly with a more efficient algorithm. I think we're still looking for an algorithm that's, with enough speed to
Well, there should be an analog to the accelerated bias coin design for that.
Yeah. And I want to finish with a personal note. This year I did an art course. What surprised me was that an art critic described Jackson Pollock's paintings very much in the same terms as we talk about stochastic processes. There's a random element and there's a trend and so on. This particular painting is called convergence.
I have one. And it's sooner this question to both speakers. So you nicely talk about convergence. But in this particular case, both of you considered only situation when there is no centers, because usually enrollment is going through many centers, and then all asymptotic properties should be somehow a little bit rethink, because you can have total n, for instance. You can have many centers, a few centers. Just imagine, we divide this n. And then asymptotics could be considered quite differently. For instance, ratio between number of patients to, say, total number should be constant, that type of thing. So did you try to do anything like that? Because it's much more randomness now. It could be still many patients, but say in oncology trials, please correct me if I'm wrong, it could be, say, 50 or 30 or maybe hundreds of centers, and it's only 2, 3, 5 patients in each center.
But is this not related to the covariate
Oh, what? No, it's not a covariate, it's still how to
Center
render.
is a covariate. Presumably, you're talking about doing stratification, right? Within
No,
centers.
I'm not talking about
You're not.
even covariates here, it's closer to what you were discussing. Randomization on treatment, and so, and in each center we have disbalance of this. So are you going to do your correction center-wise or study-wise, which is much more difficult?
Well, are you doing stratification on center? You're doing a separate randomization
Yes,
within each center.
and it's two questions. You can do either your stratify randomization by center, or it could be what they call central randomization. I prefer to call it non-stratify randomization. So did you try to do something in this direction? Just curious. Because it's another generalization. Frankly, I thought that Alessandra, you generalized your results on this case.
I think I have a paper on that somewhere.
Well,
Back in the 90s.
If I understood Sandra properly, what you said about covariates is exactly that, except that I think she was thinking of covariates with rather few levels and many patients in each block, and you're talking about perhaps hundreds of centres and only a small number of patients.
You can consider, but usually covariates are ordered.
No, let's call it blocks.
But-
Let's call it blocks.
Okay, you can call it block. So yeah, it's similar.
Do
but
people block them? I mean, do they treat those as blocking variables when they come to the
you
analysis?
can consider. But
Of course you can. And so what do people do? Some people in
But
clinical
you see, it's
trials.
addition to all, it's we have number of actually number of centers to some extent random. For instance, it could be some centers which nobody. is-
I can do all the models, yeah.
What question are you interested in? Are you interested in?
I'm interested. Did you try to generalize all these
Are you
approaches,
interested
nice
in-
optimal designs to this particular
Oh,
situation?
okay.
And because then problem of consistency.
Well, I mean, if
and
you're
all
just
this
interested
power.
in inference, these, if you're doing stratified randomization, each of those clinics is going to be independent.
You see, it should be slightly different model now. We have to consider actually, in most cases, so-called population model or random effect model. For each center, we have its own new I1
Yeah.
and new I2. So they're coming from population. So it's mixture of distributions.
So the inferential part extends to model.
Of course.
So-
I just was curious. Did you try to do something?
Regression modeling, yeah, I have a
He wrote a
paper on
paper.
that.
That's it.
He wrote a paper.
Yes, then next.
But you do
I
not-
have another question.
Sorry, yeah. This is a very general question for both speakers. It arises partly from Bill's emphasis on name and allocation. If I have normal populations with different means and variances in the ratio of 64 to 1, this is what Bill had. in his
Yes,
experiment.
I was a bit shocked by that.
But what,
yes.
what is the
mentioned
clinically
it.
interesting quantity? It must be. It can't be just be the difference in the means.
No,
Yeah.
no.
So I mean, perhaps we shouldn't do name allocation, but perhaps there's some utility function combining the two parameters that one should look at.
Yes.
And perhaps all the people who go into medical practice here could tell us what it is.
Okay, okay.
No good answer.
Okay.
Wrong question.
Wrong question or wrong
Because he can't
questionnaire?
Well, I mean, you want your slides to be dramatic, Anthony.
Sorry.
You want your slides to be dramatic, or no one pays any attention to them.
Oh yes, no, that's right. But
I'm not going to put up 1.5 to 1. No one's going to go fund it.
there is a problem. I mean, a serious non-mathematical
Yeah.
problem.
But at least I mentioned it. Right. I did say it. You're not going to get
It's,
it.
So Tom,
Nancy knows about practice. Nancy.
I was going to change the subject.
Yeah, I know you.
Do you want to talk
Please.
about
Just talk briefly about compound criteria using the harmonic mean. I think Vlad in his talk used a criterion that, if I recall, was the variance of theta hat times the probability of doing the best thing for the patient. So it's a multiplied thing rather than a sum. And has there been a lot of thought, I mean, I was going to ask Vlad how much he thought about that criteria, but that's a special case of your harmonic mean, isn't it? You're taking the product. I mean, what do you really mean by criterion functions that are harmonic means? And how much?
So you say that this
No, you
his
just
criterion function
Is a special case of a harmonic mean, right? Where you have, where you.
Is it?
So what do you mean by a harmonic,
She's not with it.
criterion functions that are harmonic means, if not products? So I don't.
Mean is.
What's
well
your
defined,
definition of a
the-
harmonic mean?
It's well defined. You take 1 over the.
Yeah, it's not a geometric mean, is it?
Or
Oh, okay. So you're talking about geometric means,
Yeah.
yes.
Oh,
I
I see.
understand.
Yes, good.
I understand now.
Yes.
Okay, no, but it's true. I mean, you can take any, there are several ways of combining, and, you know, means, geometric, harmonic, or average, are different ways. But we, in the original paper, in the biometric paper, we do talk about other ways, including the geometric mean. Yes, that's right.
So you had logarithm or you had values.
It- I think what we showed it was that if you take a geometric mean, then the compound criterion is the same as your constraint optimization. Yes, that was, I think we have a brief mention of that. Or maybe it was a previous version of the paper and the referee said that that's too trivial, take it out. Sorry.
That's probably Wendy Wang's PhD thesis. The equivalence of constraint.
Who's Wenky Wang?
He
I got it
left. He was
wrong.
here a minute ago.
Can I ask a question? So again, I'm really interested in the topic that you have. How to consider collective ethic and individual ethic and strike a balance. And we struggle along this, very much in clinical trials. So since this is the last session and for the week, I really like to have a take-home message, so I can go home happily. So again, but from your talk, I think it's still a trade-off, right? I mean, you choose the omega or whatever. Can you give some kind of advice, how to some of the guidelines? I know that there's probably no single answer. Again, when you struggle between how to strike a balance between individual ethic and collective ethic, what's the
Well, this was the idea behind doing all these little examples, numerical examples, that by looking at the final outcome and maybe doing some simulations, we would have a better idea a posteriori, if you see what I mean. It's difficult to, from a theoretical point of view, to say this is better than that. But we were looking at the numerical examples just because, to see if we were convinced by the results. And then we will say, yes, that seems reasonable. Maybe we should do that then. So no, I can't do it.
I think the thing that makes it unsatisfying is the fact that the two different loss functions are on different units of measurement. So
Yes. To
be on the same
Yes.
you can't. It's not easy to balance the two. I mean, if you could take your estimation loss and turn it into some loss of numbers of patients, or if somehow one could manipulate one into the same units of measurement as the other, then I think you would have something you could take to a physician and say, what is your trade-off? But now we have these two things that are in totally different,
so
they're just totally different dimensions. And so how do you, what does it mean to combine them? I mean, what's it mean to say alpha one plus the other?
Right. So one approach, Dan Barry and colleagues use is that you have a patient horizon, right? And then you like to treat small number of patients in the trial, and the result is going to apply to the larger.
So those are the calculations that need to be done to make the you don't think so? What do you think?
No. I just
Well,
like
he
to.
was shaking his head no.
No. I'm trying to again. I like to. We know that there's no. I mean, I like to put this kind of work in a framework such that we all communicate the same way and make progress. And I'm still come up with so one way I know how to do it is this patient horizon kind of concept, right?
Right.
Suppose in the world, that we have 1,000 of these rare disease patients, right? And then how do you design a trial? Should we design a trial with 50 patients or 100 patients or 150 patients? And how do you adaptive randomize between them such that you would like to treat the patient better in the trial, and you like to apply the information to the remaining patient such that you maximize the overall number of success. So that's one setting. I kind of agree, but again, and from the more theoretical development, like what I'm hearing, I don't know how
So
to.
I think Nancy's right. Unless we decide, what
we
is
say the same
equivalent
thing.
of a 10% increase in the variance, which we can't really know.
Yes, you could do
That's-
So I think you can, I think with the same ideas he's talking about.
These results of Berman are lost from randomization because you've got a slight increase in the average variance. You can interpret this as the number of patients on whom information is lost due to the randomization procedure.
Yes, you can.
That
you
would
can
seem
do
to
it.
be perhaps to go
The
with
answer
that.
to is, yeah.
And then
yeah.
the number of patients who are not getting the better treatment. But I think this use of loss, which is a function of the variance ratio, but it's something that, if you look at asymptotics, it disappears. Variance ratios disappear in the randomization. Sorry, perhaps this is too much detail, but the loss goes to a fixed small value, like 5 patients or something. So perhaps that's what people want to think about. You remember these plots I do in my papers, probably. It's those. But this thing goes up.
Final question, Luke.
Yes. This is a question both for you and Bill. Since you randomize, it seems that the frequency of allocation of each treatment is strictly positive whatever you do. So you should have no difficulty for the consistent. Since you randomize,
Positive, number of patients.
whatever you
positive.
do, the frequency of allocation of each treatment is strictly positive.
Yes.
So you should have no difficulty with the consistency of everything.
The inference.
No, I don't know.
It's about consistency to what, but they're interested in that, not.
Consistency of the parameters, whatever they are, and because then the probabilities are based on these parameters, there is no
Properties of the
problem.
MLE are fairly easy to show. So that's what you're talking about.
Okay,
The
I understand
actual-
what you say, that it's fairly easy
The
to-
actual asymptotic properties of
Yeah.
the design is the really difficult part. So-
In general, that's true, that's true. Yes. Yes. Not to the estimators, but it's difficult to prove results about the design, yes.
That the weights will go to the optimal weight. That's you mean the convergence of design.
Yeah.
That the weight of your asymptotically will go to the weight which you target.
Well, even the consistency isn't difficult. The asymptotic normality for some of these is difficult.
But asymptotic normality of what? Of the design or
Of the design.
or the
Yes.
parameters
The
of means?
parameter estimators, that's fairly straightforward.
Straightforward.
Yes.
Even if you plug in, when you do this randomization, by the way, I somehow missed it, probably I missed it just. You do adaptation of you see, your randomization rates depends upon the value of unknown parameters.
Yes.
So are you, in practice, what you will do recommend? So do some kind of interim calculations of these parameters and then plug them in.
Yeah,
Well, that's what we
double
were
adaptive
doing.
means.
That's what we were
Double
doing into
adapt.
into the target allocation, yes.
And everything works perfectly.
But Stephanie wants to go.
Okay, this applause for all the speakers in this wonderful session. I'm the one who has to do the closing remarks. I had prepared a couple of slides, but I'm not going to show them because I think you're all tired now. So all I want to say is that I think we had a very successful week here. Wonderful talks, very good scientific program, and good interaction between academia and industry. So in particular, I would like to thank all the speakers who contributed to this, the discussants, and the poster presenters.
Shall I keep it?
Also, all of you for engaging so much in the discussions we had, even if we overran a couple of times. But I think that's what makes the workshop such a success, that everybody was engaged and interacted and was interested in what the others were doing and what new ideas could be learned from others. I'd like to thank my fellow organizers who have left me in this position to speak to you all when everybody just wants to head out and I have to stand up here and keep you from running away. That's Peter Müller, Vlad Dragalin, Sandra Elrich, Heike Großmann and Mike Krams, who all did a huge amount of work. I'd also like to thank